Cornell alumnus. I believe he did his undergraduate study with environmental engineering, and then he moved on to do a master of engineering degree with Cornell System Engineering program. It's a very good combination of energy, environment, and systems. You can see, look at all these things. There's no better person who can talk about energy systems. So now, Liam, so please take away from here.
Thanks.
Thank you.
So as Professor Gao said, I'm Liam Boire. I'm going to be presenting on energy research at Idaho National Laboratory. So it's not very creative of a title, but I wasn't quite sure what they'd let me present on or not let me present on. So I had to go a little vague. But I'm going to do a quick introduction, a little quick exercise, ask some questions.
We're going to try some funny things here.
Oh yeah, no worries.
That doesn't work. Just go down to 5. Yeah. Okay, we'll try 5. Is that 2? Yeah, that's okay, right? That's better. So, okay. So 4 is no longer 4, it's 5.
Then I'm going to dive into a specific project that I got to work on. It was pretty interesting. And then just do a general lab overview, talk about some of the work that other parts of the lab do. We have 4,000 researchers at the lab, so it's a wide variety of projects. Real quick, on the roster, the attendance roster, on the back, there's going to be some sheets that have sign up for opportunities at INL if you're interested in internships, fellowships, postdoc positions, things like that. You can just put your name, email address, and your major, and they'll kind of direct the opportunities that are of interest to you if you sign up. And then up front here at the end of my presentation, if you want to grab some handouts on postdoc positions or internship opportunities for this summer, feel free to grab the handouts. Take as many as you want, hand them out, give them to your friends. They're not quarter cards, but they're as close as we could get. And then I'll do a quick pitch for the Geothermal Design Challenge that the lab is hosting this year. So that exercise I was talking about, does anyone know what these are? Feel free to shout it out if you know what they are. All right, well, they're distribution. One of them's distribution level glass insulator. The other one's actually a telegraph line insulator. And another quick question, do you know who came up with the idea for these?
Probably Ezra Cornell.
Yeah, Ezra Cornell came up with the idea for these. So I thought it was kind of cool. One of the projects I'm working on actually ties back to Cornell. But another question after that is how many of you have ever noticed these? Walking around in your daily lives, they kind of get blended in. They kind of, a lot of people don't notice it. But what I'm getting at here is energy is more than just what's generated, how it's stored, and how it's used. There's this big piece in between that a lot of people ignore, and it's how it's transmitted. It's how it's delivered. And so there's all these entities, all these institutions that come together from municipal level all the way up to the federal that are working to make sure that energy is delivered effectively, safely, efficiently to its end users. One of those entities is the Office of Electricity at the Department of Energy, and they have two major research programs. And under those programs, they have some projects and project labels, as they call them. There's the Transformer Resilience and Advanced Components Project, and the Advanced Grid Modeling Project are what I'm going to focus on today. They sponsored the project that I'm about to talk about. So what the DOE OE asked us to do was, they said, please assess and prioritize electric power grid equipment with regards to resilience of infrastructure. So they asked us to do this, and we said, well, we have some questions about that charge, right? What does resilience mean? And which components need to be improved, if any, right? What if the component is fine as is or is too expensive to improve? On top of that, how should we prioritize these after we've assessed them? You've asked us to prioritize. How should we prioritize them? And then I always like to throw in this question when I'm handed a project. Is there a more interesting question that we can answer along the way? So these questions are going to kind of guide the rest of the project presentation. So what does resilience mean? Here's a couple definitions. We Google it and we say, well, what does the OE, Office of Electricity, really mean? Well, the ability to recover or adjust easily to misfortune or change. Not really quantitative enough for us. We can't really do much with that definition. So we said, well, we do a lot of work with the DoD, the Department of Defense. How do they define resilience? And they're defining it in super militaristic terms. They say, support the functions necessary for mission success with higher probability, shorter periods of reduced capability, and across a wider range of scenarios, conditions, and threats in spite of hostile actions. So, I mean, hyper-militaristic and a little more specific in what we're getting at. But the problem is, what's the mission? Deliver electricity isn't specific enough because who are you delivering it to? For what reasons? With all the entities that are involved in delivering electricity, utilities, municipalities, end users, generators, they all have a different dog in the fight. They all have different desires and goals. Municipalities want their police stations, hospitals powered. They want their constituents happy. Utilities want to make money, right? So how can we balance these different priorities? And so ultimately said, hey, why don't we just let the Office of Electricity define it for us, and we'll work with that definition. So this is what they said. It's the ability to withstand small to moderate disturbances, abnormal operating conditions without loss of service. I'll let you read the rest, but this definition helped us define the problem. We worked with this definition to define failure and to define success for a resilient grid. So another quick question, which components need improvement? That's basically, yeah, that's basically what they asked us. They said here, which components need improvement? And it's, as you can tell, it's a pretty complex problem. I mean, we can see different flows, we can see generators, transformers, buses, and lines, and we're not really sure what we need to do. How do we approach the problem, right? So telling when something's working is easy. Telling when something is resilient is not as easy, but what we can do is we can tell when something's failed. So we said, all right, here's what we're going to do. We're going to define failure in a way that the Office of Electricity agrees with. We're going to calculate the importance of components in regards to how much they contribute to that failure. We're going to model the capacity of those components to adapt to disturbances and changes, just like they asked us to do. Take a look at how those results cross-correlate, and then we're going to prioritize and rank those components. So for those of you who are interested, the importance of components is the Fussell-Vesely importance measure. It's a probabilistic risk assessment measure. It talks about the sum of the failures associated with a component divided by the total failure probability of the system. It's basically how much does that component contribute to possible failure scenarios for the system. You can look it up. There's more mathematical definitions, and there's actually a lot of importance definitions, but this is the one that our sponsor tied to and said this is what we can really use to focus our research in the future. So that's the one we chose. So we defined failure using our Power World model. It's just a simple simulation and visualization tool for transmission and generation and transmission. And we used it to define our N-1 and N-2 contingencies. So what combinations of components, combinations of 2 and 3 components can cause the system to fail. For our electric grid, they have a requirement that any one component should not be able to fail and fail the entire system. So we ignored the one component failures because they're impossible in these scenarios. So we looked at the N-1 and N-2, so the groupings of 2 and 3 components. And we stopped there because the more components you add to your failure cut sets, the less likely they are. So if you have a 10% chance that a component's going to fail, if you need 2 of them to fail at the same time, you're at 1%. If you need 3 of them to fail at the same time, you're at 0.1%, 4, et cetera, et cetera. On top of that, we're exponentially increasing our computational time required if we are increasing the number of component cut sets we need to evaluate. So DOE, OE said 2 and 3 is enough for these large systems, and likely beyond that, maintenance is going to handle any of those likely failures. We passed that cut set information into Sapphire. It's a probabilistic risk assessment tool. It's based on fault trees, and all we did was we modeled those component combinations and the probabilities of failure for those components based on generic North American grid data. So how often do transformers fail in the United States? That's how often we chose to make them unavailable in our system and calculated the probabilities of those failures occurring. And we use those probabilities to calculate the importance of the component. So how much does this component contribute to grid failure? After that, we used the powder tool. This was developed by the lab by a couple researchers, really interesting researchers in resilience. If you want to look them up, Craig Rieger and Tim McJunkin. They do a lot of work with resilience and cybersecurity, control systems and things like that. They're working on quantifying resilience. And in that vein of research for quantifying resilience, they said, let's try to find a way we can model how well a component or group of components, in this case it's considered groups of supercomponents, how well they can respond to disturbances. So we look at the real and reactive power over time of a grouping of components. And so, for example, generators produce a certain amount of real power and reactive power for the grid, and they ramp at different rates. So a generator may have a different ability to adapt to a load being added to the grid or dropped off the grid. Same thing with like a synchronous condenser. It only adds reactive power to the grid. How much can it do at a given time depends on its inertia and things like that. So different groupings of components allow for different flexibility of the grid to take voltage disturbances and things like that. So we wanted to look at probabilities, how often do these components fail, but also can they take minor voltage disturbances or major voltage disturbances? How can we calculate that? So this tool gave us an idea of how flexible the components were. And so this is ultimately what we came up with for our answer, which components need improvement. We looked at circuit breakers, generators, lines, and transformers ultimately. And what we did was we ranked the components by importance. All the components in the system, there are about 1,200 of them. And circuit breakers made up the first 14 or 15 or so. So we said circuit breakers are probably the most likely to lead to failure in this case. Generators, since there's only a few of them, there's only 25 or 30 in the system, they contribute a lot of power to the system. Each one does. So if one goes out, it's likely that there isn't enough power to sustain the system. Lines are important for distributing power. They're important because if one goes down, all of that load needs to be reconfigured to carry it on, or it just needs to be cut, which would be a failure. And then transformers are also important. But the problem is there's a random chance that any of these components could end up at the top, right? If you take a random conglomeration of components, and circuit breakers make up approximately half of the components, what's the likelihood that the top 10 are circuit breakers? It's actually pretty high that randomly they come up at the top, right? So how do we know that it's circuit breakers specifically that need to be improved and not just a random chance? And so we looked at alternative ways of considering the data. And one of those alternative ways was the sum of the importance. So if a component comes up a lot in the system, it's possible that it contributes a lot to system failure, right? So by summing the importances, we were able to take into account how often a component was encountered in the system. And then by comparing the magnitudes of these numbers, looking at the number on its own means absolutely nothing, but you can compare the relative magnitudes of the numbers and say circuit breakers make up more than half the system, but control panels, there's an equal number of control panels, but we see almost a 2-order of magnitude difference between the sum of their importances. So clearly, it's not just the sheer number of circuit breakers that are causing it to be this important, because control panels would be right next to it if that were the case. But then we say, well, we don't want to over-account for overabundance, right? So circuit breakers, there's a lot of them. If we had a system that was 99% circuit breakers, of course they're going to have the highest sum. So what if we looked at the average, right? If we looked at the average, circuit breakers are still in the top 4, but we have generators, transformers, and lines. And ultimately, what we did was, because this is a new method of analyzing systems, we weren't sure which was the best, nor has this method been validated yet. But if you take a look at the top grouping of 4, we have circuit breakers, generators, lines, and transformers. If you look at the sum, it's circuit breakers, generators, lines, there's control panels in there, but 5th is transformers. And if you look at the average, generators, circuit breakers, transformers, lines. So ultimately, it's going to be one of those 4. Likely it's not control panels because they're extremely reliable. So the fact that they're showing up in this sum is probably purely due to the fact that they're highly abundant in the system. So we said generators, circuit breakers, transformers, and lines are the components that need to be improved. And when we went to our sponsor and said, hey, this is what you guys need to focus on, they said, that's great. How do we improve lines? They're a conductor that's wrapped in an insulator and they're strung between 2 poles. There's really not much we can do on the material side of things to make them more resilient or more reliable. The best thing we could come up with was, well, we could come up with an easy deployment system. So if they go down, you can easily string them up again, right? But our sponsor is more interested in technological changes, materials changes to the actual systems and components as they exist. So we said, all right, maybe we don't focus on lines for our next project. With generators, we had the opposite problem. Rather than being too simple like lines, generators are extremely complex. A generator in this case stands for the average generator in the United States. So that's a conglomeration of coal plants, hydro plants, gas-fired, nuclear. Every generator that works in the United States is captured in this number. And so if we wanted to find out what's causing them to fail, we need to break them apart, decompose each type of generator and say what are the things that are causing them to be unavailable, right? So that's a whole nother project of this scale or larger, and so that doesn't quite give an answer, but that can be used later. Maybe we can dive into generators later.
So can I ask
Yeah, sure.
So unavailable has a time component to it, right?
Mhm,
So
that's
is
right.
that did you select like a baseline in terms of how long to use in this model?
Unavailability was directly translated into the failure, the probability of failure. So rather than saying we're running the model for a year, if you run the model over any time period because of the unavailability data, the magnitudes of the unavailability data, it comes to a steady state.
No, but I was thinking not time scales on that order. I was thinking time scales on hours.
Yeah.
The generator might go down, but it doesn't mean it's failed. It's unavailable.
Right. So
is there some kind of benchmark that you use to capture that element?
So when a generator's failed, or when a generator is unavailable, it's no longer producing power for the system, and that lack of power production can cause other instabilities in the system that cause failure. That's what we're accounting for. If a generator becomes unavailable during the modeling process but doesn't cause a system failure, it doesn't get accounted for in the summing, if that answers your question.
One thing, Liam, if the generator has a capacity factor which is, let's say, 80% and 20% of the time it's not functioning, so does that make the probability less of something happening to it because it's not working 20% of the time?
So that would. In this case, this is highly genericized data. So we used IEEE 2007 gold standard data for the probabilities, the unavailabilities. And so that's literally taking every generator in the United States with average maintenance and averaging out all of those capacities. If we did dynamic modeling for a specific system, which we're working on for validation of this research, then yes, it is absolutely going to affect those probabilities. And so we're working on how can we, more specifically affect those probabilities to account for like capacity factors and things like that.
Liam, you can tell us to stop asking questions.
Sure.
But,
well, we got time.
In the term of resilience, to me, it seemed like was embedded in the OE definition includes sort of natural events that could occur and
That's right.
cyber intervention.
Absolutely.
Tell me how you're handling those two.
Yeah.
A hurricane, a flood, something like that that wipes out, or some inadvertent thing knocks out a transmission line or something like that. That's different than technical failure of a company.
Yeah,
right?
that's right. So the only way that's being, to be frank, the only way that's being captured in this analysis is if there has been a cyber attack in the United States that has taken out power, it's accounted for in that unavailability data. When it comes to control systems resilience, that's a separate aspect. We specifically chose not to look at control systems for this resilience exercise.
Sure.
That's right.
Okay,
So
thanks.
we have different aspects of the lab that are working on control system resilience. So that will be overlaid eventually, but not at this time.
Right.
Okay, so final verdict, we got to look at circuit breakers and transformers. So that's cool, I guess, right? This is the components that need to be improved, and this is how you can look at it. But that leads me back to my question I always like to ask when I'm handed a project: is there a more interesting question we can answer? And I found out that there was a more interesting question. This is the results from the importance measures, just the top 5 important components of the system specifically. So these are specific components. This would be, say, circuit breaker A on bus 9. And there's 500 circuit breakers across the system. This is one of them. And then on the right, we have the adaptive capacity of those components. So how easy is it for these to take disturbances? Or in this case, this is how adaptive are they? These are the components with the lowest adaptability, right? They can't take any large fluctuations, essentially. And what we find is components that are most likely to lead to system-wide failure are in the top 5. We have 2 circuit breakers on bus 9 and a circuit breaker on bus 10. So those are the most likely that if they fail, they're going to lead to system-wide failure. And we also find that buses 9 and 10 have the lowest adaptive capacity. So what this means is voltage instabilities for buses 9 and 10 can cause small voltage instabilities can cause the bus to fail, right? So a small voltage instability could cause the circuit breakers to trip, right? Okay, so what does this mean? I showed this graphic before with no circles on it, asking what components need to be improved. Well, buses 9 and 10 are in red. Those can't adapt well to voltage instabilities. And the circuit breakers on them, if they fail, they are likely to lead to system-wide failure. The circles, the blue circles, are circling other components in the system that, if they're failed simultaneously to the circuit breakers on bus 9 and 10, lead to system-wide failure. So basically, I can cause a minor voltage instability on bus 10, and I can also, let's say, force a switch, maybe with a cyber attack, on the lowest blue circle, and the whole system goes dark. That's what this means, right? So if that's not impressive enough, this is the IEEE 118 bus model. For those of you who don't know, the IEEE 118 bus model was modeled off of the 1967 United States Midwest transmission grid. So had I known this in 1967, you can make the whole system go dark. So this is the kind of analysis we're working on. Now we know maybe we need to include some kind of adaptive capacity in buses 9 and 10, or maybe we need to reduce or increase the cut set length, so include more components, more parallel components to the cut sets for buses 9 and 10 and these other blue circles. There's many ways we can improve it, but the number one thing is we can just start improving the circuit breakers so they don't fail as often, or improve transformers so they don't fail as often. So I was pretty excited by this, as were the other researchers. It's kind of a dark note, I suppose. 50, 60 years ago, it's a pretty shady thing. But the transmission grids changed a lot since then. The components in it have changed, but and the configurations, the adaptability in terms of ways we can switch routings, and the new lines that have been put in to carry more power. And things like that make it a little more flexible. So this doesn't hold today, but we can do this kind of analysis on grids today, which is what we're working on as a validation exercise for this research. I guess I can take questions on this. I have more for a general lab overview, and I can take questions after that as well. But if anyone has any dire questions on the specific research, I can take them now before moving on to the lab overview. Yeah.
So you mentioned the fault tree analysis earlier. Of course, with this, for fault tree analysis, one of the key things is this top undesirable event.
Mm-hmm.
And in the end, you want to quantify the probability of that event.
Mm-hmm.
Of course, as you can see, the tree, you are going to have a lot of different branches. In the end, they are going to be all together.
Mm-hmm.
So how did you, because I can imagine all these things are interrelated. There is a lot of correlations of all these different possible events. So how your team was able to deal with this correlation, but in the end also come up with a probability that you feel makes sense?
Yeah, okay. So that top event, that fault tree event, that failure event, was defined by system-wide failure. So that's defined through those voltage instabilities in our flow model. Voltage instabilities are unsolvable cases by our flow model in PowerWorld. Additionally, PowerWorld has an awesome contingency analysis tool. So it's used by transmission companies and distribution companies, utilities, to say, if we need to take this line out of service, how can we, are we still meeting our N-1 contingency requirement by FERC, right? So are we still meeting our requirements? And so they can enumerate, that tool can enumerate the cut sets for the system, and then it can give you a list of minimum cut sets, so basically not repeating unnecessary cut sets in that sense. So we defined our failure very explicitly, and then we used PowerWorld to enumerate the combinations of component failures that met that failure mode. Then we applied generic transmission unavailability data from IEEE onto those component combinations to give us the probabilities of those failures, and then we can sum and aggregate.
Great, thank you.
Yes?
So I'm wondering, in your research, do you consider any economic or political implications of the findings, or you just do the technical piece?
Yeah, so the question was, do we consider economic or political implications? We didn't in this case. So we were charged by OE to pick the components that need to be improved. We didn't in this case. However, Powder, the last tool I talked about for adaptive capacity, was originally designed with economic utility in mind. So the creator of it actually deems these supercomponent combinations as economic units. He literally calls them that. And that's the idea that there's an economic utility tied to those groupings of components that can be calculated or quantified somehow with overlays of this is an industrial process that's happening here that does this for our community, et cetera, et cetera. That wasn't considered in this case because this is a genericized system to prove an approach, but it is considered in some of our other projects. Yeah.
And maybe you're going to get to this when you talk about the other parts of INL, which I know a little bit about, but
Yeah.
The issue of reliability at the level where it's a very critical thing to a subset of drawing power off the grid has also different time constants. I mean, the way they'd solve it is if they know there might be failure, they'll put a UPS in, take care of the electricity. But
That's right.
I know the lab is also doing sort of hybrid systems now with combined heat and power, and there's very different time constants to that because you have thermal mass, and you can't shut the heat off for a week. But it's very. Is that something of interest to your group, or is the lab must be tackling that?
Yeah. So
that's outside of just office for electricity.
That's right. That's right. So the lab and people in my group are working on situations where that comes into account. Not so much in this research because it's just electricity is pretty quick as far as timescales go, and its failure is just the system goes dark. It's not. You can choose to define failure however you want. Maybe the system has to go dark for 24 hours or 48 hours or something like that, which you can account for with mean time to repair included in your unavailability data, which it was in this case, but we didn't account for timescales after the failure. I mean, there is a lot of work at the lab looking at those differentials and timescales, and part of the powder model, again, the powder model is those miniature timescales of ramping and real and reactive power, how they can be accounted for. If he was trying to pull heat onto that for his economic analyses, then I imagine he would have larger timescales for the heat.
Okay, so and the other piece, which I think you might get to too, has to do with the trend toward electrification of vehicles, and all of a sudden we change the load structure.
That's right.
And that's got to be of interest, I would say, to
Yes.
the lab. And that seems to me it does fit in your space. So are you tackling that too? Where
Yes.
all of a sudden everybody plugs in their
Right.
Tesla at night or something.
Yeah, absolutely. It's actually housed in the Advanced Transportation Technologies group, but a lot of other groups are looking at it because it has implications for national and homeland security and emergency response as well. So if everybody's got their charged cars and the power goes out, can they use their cars to help power their homes or power necessary services? Or if we need to, can we drive these electric vehicles to a hospital and power life-sustaining services and things like that? So it's looked at across the lab for sure. The Advanced Transportation Group is the one that's really diving into that. But we also have microgrids and I forget the system they use is called RTDS. I forget what group. I think it's housed in Power Systems. Real-time RTDS, data system, real-time delivery system, something like that. And it's grid modeling. And they're looking at what about this? What about that? Let's plug in 30,000 Teslas to Jackson Hole's electric grid and see what happens, kind of thing. Yeah. So it is being looked at, and I don't get in too deeply about what we get to at the lab. I'm going to talk in broad terms, but I'll get a little to that. And then the handouts there, I was actually using them when I was talking to Professor Gao. They talk about, one of them's talking about our internship categories, but those internship categories are broadly aligned with research subcategories of the lab. So advanced transportation is one of the categories listed there, clean energy and technology, nuclear fuels and materials, things like that. All the stuff that we work on at the lab is also listed as subcategories for internships. So that's actually, it could be a useful handout.
It's a hugely well-kept secret that I've had the privilege of going to Idaho a lot for the past 15 years or so. And I mean, they have virtually everything there if you're interested in this energy space. I mean, there's certainly a good battery testing group.
Absolutely.
I think that many in this room would be interested in the feedstock logistics for the biomass people is there, and this incredible stuff that's being done with electricity now is a big feature for. So it's a terrific national asset.
Yeah, it's awesome. Yeah, and it's a pretty well kept secret, I would say.
It is. Yeah.
So I'll just transition to the general lab overview. So I thought I'd start with why. Our mission specifically is discovering, demonstrating, and securing new nuclear technologies, clean energy options, and our critical infrastructure. That's what we do every day. Basically, if you're doing a project at the lab, you can easily, very easily, point a direct line to one of these three major pieces. Our official motto is to change the world's energy future and secure our nation's infrastructure, critical infrastructure, and you know, that is what we do. That's our motto, but I really prefer our unofficial motto, and it really helps guide a lot of whether we should take our work or shouldn't. It's we do what others can't, won't, or shouldn't do. Can't in terms of impossibility, won't in terms of profitability, and shouldn't in terms of safety and national and homeland security. So we get to work on the stuff that no one else, literally no one else can or should work on. It's really a lot of fun being able to do that. And what I believe personally is I'm working there. The reason I'm working there is because I get to work on cool projects across the spectrum of the lab space. So whether it's, you know, working for the DoD on their drone programs, or for the Air Force on their base resilience, Office of Electricity on their resilience, launching a first-of-a-kind nuclear reactor. We just built the program execution plan for that. That was released in December. So I get to work on a variety of projects that are, you know, world-changing in a sense, and I can see the impacts of them in real time. And not only do I get to work in a world-class research institution, I get to work in a place that's absolutely wonderful. I'm sure Professor Tester can attest to how beautiful Idaho really is. I mean, it's called the Gem State because of the opals, but it's really the Gem State because of how awesome it is there. I mean, Idaho Falls is 2 hours from Yellowstone, 2 hours from Grand Teton National Park, 3 hours from the Sawtooths. It's an awesome, awesome place to live as well as work. So that's why I like working there. And how we do that is fostering collaboration, and I like to say sometimes friction, between these world-class minds, both at the lab, universities, and industry partners. We get to work with really cool stuff that other people don't get to work with, and we're doing it to research, demonstrate, deploy, develop new technologies that sometimes people don't ever get to see, and sometimes you might be using in 5 or 10 years. It's pretty amazing. So the what we do, we're roughly categorized by 3 major pillars. We have a nuclear pillar, national and homeland security pillar, and clean or energy and environmental. So those are all our science and technology directorates, and we have some operations research work in our advanced test reactor for nuclear fuels and materials, and our material and fuel complex out in the desert. So those are kind of operations side of things, but our main science and technology work is nuclear, national and homeland security, and the energy and environment. So for the nuclear, some examples of some of the stuff we do. We're developing accident-tolerant fuels. That's really interesting work. It's really helpful for improving the public's view of nuclear. If it's accident-tolerant, you're not going to have to worry about it, right? So we don't have this Homer Simpson's our safety chief kind of thing going on. We have doesn't matter if Homer Simpson's doing it or if nobody's doing it. If something goes wrong, the fuel can tolerate it. We get to demonstrate a first-of-a-kind small modular reactor. That's the first-of-a-kind reactor I was just talking about. We worked on a program execution plan for it in December. It'll be finally constructed in 2027 and ready to use, ready to research. That's really cool. We're prototyping a very small modular reactor. Yeah, I know they have some really creative names here. Small modular reactor, very small modular. We're working on micro reactors, go figure. But besides the uncreative names, it's actually really cool technologies. We're always working on improving our modeling and simulation capabilities. We're really working towards how can we design nuclear reactors digitally and test them digitally before we even start digging. Because as soon as you start digging, you've made a $1 to $7 billion commitment or more. Prior to that, you have all the play and fun you can on the computer. Testing our advanced materials and fuels, and then the advanced test reactor, transient test reactor, and then the radiothermal generators. Those are the space batteries. We build all of them for NASA. Everything that goes into space that has the little space battery for rovers, probes, and things like that, that's all built and launched, or built from the lab. For national and homeland security, it's analyzing homeland security solutions. It's a lot of resilience work. We get to manufacture the Abrams tank armor. That's all depleted uranium that's built and manufactured at the lab. Improving cyber, that's a really big thing. Cyber resilience and cyber control systems is huge at the lab. We just have huge investments in our cyber integration center and computing collaboration consortium, CCC. So those are buildings that are going to be up and running in end of 2019, 2020. We're going to be taking students and researchers, university collaborators, professors, and things like that, putting them all in one space and tossing challenges at them that no one's ever dealt with before. Yeah, oh, and we have the National Cyber Incident Response Team. That's really cool. It's the HUNT team. We have basically a cybersecurity hotline for all of our critical infrastructure. So if something goes wrong with, say, a chemical plant or a nuclear plant and they suspect it's a cyber attack, they can call our lab and speak with our cybersecurity researchers. They'll step them through. If they can't be stepped through the problem, our researchers actually deploy to the location and deal with it on site. So, I mean, that's pretty cool. It's heavy work. They work in a building with no windows and pretty much no one's allowed in but those researchers, kind of thing. But it's pretty impressive watching them deploy. It's like a fire truck or police cars going by. It's like they're just out and going. It's very impressive. And finally, researching and analyzing some of the malware that's floating around the net. And then energy environment, I'm sure there's a lot of interest in that for this class specifically, and it's actually the directorate I work in. We get to address those energy production challenges that I alluded to early on. Modeling the integration of renewables, this is a big problem now, and I'm sure you're all aware. The sun's not always shining, and sometimes it shines too brightly for what we're prepared for. The wind's not always blowing, and sometimes it's blowing a little harder than we're prepared for. How do we deal with that integration? How do we store that power? How do we properly meter and control all of that is a pretty big problem. Analyzing demand response options, water utilization, things like that. All of this is work that's done across the lab. I mean, I'm putting 3 or 4 words on a bullet here, but each of these bullets is probably 2 or 3 or more research teams working on different projects trying to address these problems. The biomass and bioenergy feedstock assembly is an enormous lab. It's the Energy Systems Lab. It's huge. They have milling machines and all these different kinds of feedstocks that they're testing the energy densities for, and how does it flow through this better, or can we crack it with pyrolysis? Can we increase its density by converting it to a biofuel? What's the best way to convert it to a biofuel? Can we generate new microbes to help us break down these components? It's a really fascinating lab, and there's always something going on there. And then the one that really surprised me was the energy critical materials. I didn't really know what that was when I first came to the lab, but I sit close to the main researcher and postdoc that does that kind of work. And the critical materials are materials that are not necessarily overly abundant that we require for certain energy technologies. So they would be like magnets in some of the wind turbines, or they're used in smartphones or electric vehicles a lot. And the problem is we have all of these highly laudable goals of converting to fully renewable power with wind turbines, let's say we'll do 30% from wind turbines and things like that. And different states have these different goals. If you accumulated all of the critical materials required to produce all of those wind turbines for how they are currently designed and built, it would exceed the capacity for the United States to produce those materials. So we don't have enough neodymium, let's say, to make enough wind turbines to meet the goals that all the states have set for their renewable energy technologies. It's something I'd never thought of. It's like, yeah, it's great, let's do 30% penetration, but it's not technically feasible. I don't know if that's the actual number, but the actual number is not technically feasible. From United States numbers, what are the impacts on national security if we're dependent on China for all these critical materials, and what are they doing to the environment over there to get extract these critical materials, and what is that doing to our environment when it blows across the Pacific? It's actually a really complex question and a really interesting question that I didn't even know anyone had until I went to the lab. Quick spiel on some of the workforce opportunities. We hire pretty much any and all STEM. We actually have an economics PhD that signed on a couple years ago. And that's new and exciting and a growing area for the lab because they realized, we got to understand incentive structures if we're going to understand people's behavior. But we hire people from obviously energy systems and nuclear engineering, chemical engineering and control systems, all the way to systems engineering and wireless communications engineers. If you have a STEM degree, they're interested in it. So it's pretty great. I mean, there's always a spot for everybody, especially mechanical engineers and material scientists. Pretty much any group requires mechanical engineers and material scientists because of the nitty-gritty of what we're getting down and doing and building. So that's just a quick spiel on the workforce opportunities. And then the pitch, I promised my work office neighbor. I owe everything to her, so I figured I'd help her out a little bit and pitch her geothermal design challenge competition. She's the organizer for it. So they have a 2019 geothermal design challenge. It's focused on data visualization, data analytics. You get a set of data and you have to answer their questions and create a compelling story with the visualization. And it's due April 10th, 2019, groups of 2 to 3, and it's anyone's participating from high school up until graduate degrees are encouraged to participate. That's all I really know about it. I can give you Phyllis's contact information if you want to contact her, or you can head to the website. There's a lot more details there.
I can give you some history here. So Cornell actually, in the first one that was launched, got into the finals on this, and there were 2 teams, both got selected. One was mainly grad students, the other were undergrads, and they got to go and visit a number of locations, and it was really helpful actually to where they headed. We didn't win the overall thing, but we were in the final 4, sort of like the equivalent of the final 4 in a sense, but it was a great experience for them. And it might just seem like it's a prize, but it's more than that because of the way DOE involves you with the ongoing program. So
that's right.
This is a good thing.
Yeah, so dive into that if geothermal is interesting to you. Even if you don't know a lot about geothermal, something Phyllis was trying to push for me to understand was they don't just need people who understand geothermal. They need people across the disciplines to tackle this problem because, I mean, people who know geothermal have been working on these problems for quite a few years. Let's give it to some statisticians or data analytics people. Or, I mean, when it comes to visualizations, you can have fun with art majors if you want, pull an art major onto your team and say, hey, how can we make a compelling case with this information, right? And I'm not joking, seriously. Some of the visualizations that won in the previous competitions were insane. Made the case very clearly and compellingly, and they talked about all the work they did in trying to piece together, how to understand how people visually interpret things. So there's a lot more to it than just understanding, how heat in the ground works. So with that, thank you. Here's a quick photo pitch. This lake is an hour from my house. That's my dog looking over. It was an awesome day. Diving ducks in the lake. Literally a bald eagle was flying over before we took this picture. I swear, like literally a bald eagle was flying over. Moose track, elk track along the trail. It's just a 4-mile hike, and it was awesome. And then on the right is the Grand Tetons. I went backpacking this summer. I mean, it's not just a great, cool place to work. It's a great and cool place to live too. So, thanks. My contact information.
I think we do have some time for questions.
Yeah, please.
What influenced you as an undergraduate to study systems engineering?
When I was when I was starting to finish up my degree, I was looking at I think it's called the Sustainable Energy Systems or maybe Renewable Energy Systems minor. And one of the required courses for that is the introductory course to systems engineering. It's one of the options you can take. And so I decided to take that. It looked a little interesting, and Professor Schneider was a very compelling professor, and it seemed like the information he was providing us with would help us solve pretty much any problem we encountered, any engineering problem we encountered. And I was just fascinated by the power that was essentially just handed to us with systems engineering. And so I was interested in the degree. And I think the final push came when, with the election and the change of administration, I wasn't sure exactly what environmental engineering would look like in 2017 and beyond. And so I said, hey, maybe systems engineering is a great way to tee myself off. They talk about the T-shaped engineer. You have the depth with one of your areas of study, and you get breadth with another. And so systems engineering was a great way to get that breadth, make sure I can attack and tackle any problem I wanted to. And so that's what brought me to the program. I mean, it was a bunch of different factors. But if you haven't taken I don't know if he's still teaching it, Professor Schneider's course, the introductory course. If you haven't taken it and you have the space in your schedule, absolutely take that course. You don't have to become a systems engineer after taking it, but you'll accidentally will be. You'll understand things from a much better perspective than you'd ever imagined. We kind of get siloed sometimes, and depth is great for when you're solving very specific, deep problems, but sometimes you're handed a problem that you don't know what to do with. Systems engineering helps step you through that process really, really well.
Other questions? So I guess with that, I think we should thank Liam again. Of course, if you have other questions, you can kind of come up. Definitely make sure to pick up the handouts so that if you are interested, of course, you write down his email address.
Yep.
Right? If you have